Hello, I'm Jerry Rechtenwald. I'm going to describe a simple experiment for measuring heat transfer coefficients. First, some motivation. Suppose we have a light bulb that's connected to a dimmer circuit, as diagrammed on the right side of this slide. Suppose further that this light bulb is in an airstream with a constant or uniform velocity of U infinity and a uniform temperature of T infinity. If the air temperature and air velocity remain constant, what happens to the temperature of the bulb as the dimmer on the light bulb is adjusted from brighter to darker and back again? We want to know, how does the temperature of the bulb respond, not just the brightness? We consider the light bulb to be a resistor, which is true if the light bulb is an old-fashioned incandescent bulb. We can make some adjustments if it's an LED source or others. For simplicity, though, let's just consider this to be a power-draining resistor that gets hot. The hot in an incandescent bulb is sufficient that it actually gives off some light. The power dissipated by this bulb is V squared, where V is the applied voltage, divided by R, where R is the electrical resistance. So we can change the brightness of the bulb by changing the applied voltage. Now we can conduct, at least in our head, we can conduct this experiment. We keep the air velocity, U infinity, and air temperature, T infinity, constant. This is the air that's flowing past the light bulb. Which of the plots at the bottom of the page, bottom of the slide, describe the relationship between the temperature of the bulb, assuming we could define that suitably, the temperature of the light bulb, as a function of the power input? Choice A suggests that the temperature is independent of the amount of power given to the light bulb. B suggests that the temperature increases linearly with power, etc. C, a decrease in power. D, a nonlinear increase. And E, a nonlinear decrease. What does your common sense experience tell you is the dependence of the light bulb temperature on the input power when the air velocity and air temperature are constant? Well, I would argue that one of the three diagrams on the bottom of the slide is probably true. Option X wasn't in the original set of choices. Our common sense tells us that if the airstream is constant, that is, the velocity and temperature of the airstream is constant, increasing the power to the light bulb will make the light bulb hotter. We don't know whether that temperature is linear with power, or whether it increases increasingly so, as in option D, or whether it sort of tails off, as in option X. We have an apparatus that allows us to explore this relationship, so we're not going to use a light bulb. Rather, we're going to use a small acrylic duct with a heat sink in it. A heat sink is used in a variety of applications, and really the goal of a heat sink is not to magically suck heat out of something, as its name might sound, but rather to increase the area through which the heat may be dissipated. So it's basically an extended surface. Here's a cartoon that simplifies the apparatus to its essential components. There's an acrylic duct. That way we can see what's going on inside the duct. There's a fan mounted at one end of the duct. The fan is controlled by a DC power supply, so we can actually easily control the speed of the fan by adjusting the voltage applied to it. The heatsink itself is attached to a thin board, and that's held in place in the duct. Embedded in this assembly is a power resistor, which is going to act as our heater. The power resistor is securely attached to the aluminum heatsink. Also, in the base of this is a thermocouple, which is a sensor that can detect temperature. The heatsink is made of aluminum, so it tends to have a uniform temperature because the aluminum has a high thermal conductivity. The power resistor supplies heat. Heat is conducted through the fins, and the relationship between the nominal temperature at the base of the heatsink and the power input as a function of other variables is what we're interested in this experiment. To return to our motivating model, the light bulb and the heatsink experiment are similar. They both consist of a source of adjustable heat input, the dimmer in the case of the light bulb, and the power applied to the power resistor in the case of the heatsink, and both are cooled by a flow of air. The heatsink apparatus is preferable, though, for an engineering experiment because it allows more control. The power resistor allows us to easily control the power dissipation by controlling the voltage to it. The airflow is confined by the duct walls, therefore it's not influenced by air currents out in the room, at least not substantially. The fan allows us to control the air speed in a controllable way, so therefore we give the device we're studying, the heatsink in this case, controlled and repeatable environmental conditions. The aluminum heatsink itself is highly conductive so that it has a more uniform temperature distribution. Therefore, we can measure the temperature at the base and get a pretty good indication of the average temperature of the heatsink. The goal now is to figure out which of these trends is true. Which of these trends, temperature versus power input, characterizes the heatsink. We have a qualitative sense that the temperature will increase with power, but is it linear? Does it increase in a sort of ever-increasing way, or does it tail off? The basic procedure now is to choose a fan speed and keep that constant. We apply a known voltage to the heater, or the power resistor, and we measure T, the temperature at the base of the heatsink. That's a single data point. By keeping the fan speed constant and then varying the voltage input, then we can measure T at a series of power settings and then get the data for the plots shown in the slide. There are other experiments, though. This is not like a right-wrong experiment to do. It's just this is one way to organize it. We could instead hold the heater power constant and vary the fan speed. That's also very interesting. In other words, can we increase the cooling in a controlled way by increasing the fan speed? We could also change the direction of the fan. This apparatus that I showed you allows us to the fan is in a pocket, and we can loosen some screws and easily slip the fan up, twist it around, and put it back in the pocket so that it blows in the opposite direction. We can also move the heatsink assembly. The entire heater, heatsink, and sensors are on a little board that has notches on it, and we can move that assembly along the axis of the duct. And so we could study the potential influence of location in the duct. We're going to stop here. This gives the overview of the basic experiment. There'll be another video that talks about the actual experimental procedure, but this gives you a sense of what we're working with.